Hey guys, in this video we'll talk about optimizers, and these are the algorithms our neural networks use during the training process to update the learnable parameters. Just a small recap, our neural network has these weights between the connections and biases in the connections that are tweaked during the training process, and these are the learnable or trainable parameters of our model. In a previous video, we talked about the training of an artificial neural network. We saw that during training, the model may use stochastic gradient descent to update these learnable parameters. Now, SGD is one way we can update these parameters, but it's not the only way. In this video, we'll discuss different ways to update these parameters, and these algorithms are called optimizers. While these optimizers all work in different ways, their goal is the same, and that's to minimize the loss for our model. Optimizers try to find the right configuration of weights and biases for a model that will lead to a minimal loss. But since the loss is determined by the network's outputs, the optimizer iteratively updates these learnable parameters without any knowledge of what their ideal value should be. So we can imagine that these algorithms are trying to find a global minimum or a good enough local minimum of a curve without knowing what the curve looks like. To explain how these algorithms work, we'll use this graph as an example. Let's imagine that this graph shows the loss function for our model, and we have our weight as a learnable parameter on the x-axis. Our graph has its global minimum here at the bottom, and this represents the minimal loss for our model, meaning the weight at this point is our desired value. Our loss function also has two local minima points, and while at these points the gradient for our loss function is 0, they don't represent the overall global minimum loss for our model. The graph we're using here is in 2 dimensions because it only focuses on the effect that the value of one weight has on the loss function. But since a real network has multiple weights, its loss function graph will have multiple dimensions. We'll use a 2-dimensional graph in this video because we'll focus on how these optimizers update one weight in our examples to keep things simple. Now the first optimizer we'll talk about is gradient descent. To update our weight, this algorithm computes the gradient of the loss function with respect to the weight of m samples using backpropagation. It then takes the average gradient of our loss for these m samples and multiplies it by our learning rate. This value is then subtracted from our old weight to give us the new weight. Because gradient descent takes the average derivative for all training samples with each epoch, it tends to move smoothly towards the minimal loss. While updating the weight with an average of the derivatives from all samples in our dataset gives a smooth movement towards the minimum. These derivative computations are expensive, which is one major drawback of using vanilla gradient descent. The second optimizer we'll talk about tries to mitigate this issue. This optimizer is stochastic gradient descent, or SGD for short. This is a variation of gradient descent that computes the weight update by taking the derivative of our loss with respect to our weight, and it subtracts this value from the weight to get the new weight. The main difference between SGD and vanilla gradient descent is that SGD updates the weights using the derivative from one training sample instead of taking the average derivative of all training samples, meaning SGD is a lot less computationally expensive compared to vanilla gradient descent. This benefit comes at a cost though. Because SGD does not take the average gradient in its weight updates, the movement towards the minimum tends to not be a smooth one. With the frequent weight updates that come with every training sample, our model's convergence towards the minimum tends to be noisy. This is because some of the samples have slight anomalies in them that make their movement different from the general movement of the entire dataset. Vanilla gradient descent does not have this problem because it takes the average gradient of the dataset. However, we've seen how computationally expensive that can be. Our next optimizer tries to strike a middle ground between gradient descent and SGD. This optimizer is mini-batch gradient descent, and the way it works is that it computes the gradients by taking the average gradient of a subset of the entire dataset. Instead of computing the average gradients for the entire dataset like gradient descent does, it takes only a small batch of samples from this dataset. This tends to be more computationally efficient than vanilla gradient descent while not being as noisy as SGD in its movement towards the minimal loss. A major drawback with all the optimizers we've seen so far is that the learning rate in all these algorithms remains constant throughout the training process. This learning rate value is set beforehand, and if we pick a large value for our learning rate, our model might converge to a solution quickly, but we might end up in a situation where we cannot reach our solution because our model skips over this point because of the large learning rate. A learning rate that is too small also has problems. You'll notice that in our example here, our graph has a local minimum point. The gradient of our loss function with respect to our weight at this point is 0, which is similar to the gradient at the global minimum point. When the learning rate is too small, these gradient descent algorithms may converge to a local minimum instead of a global minimum. And a small learning rate means that our model will not be able to escape the local minimum point once it has converged to it. While a large learning rate might be able to skip over this local minimum point, we have seen that it may also lead to our model diverging from the global minimum. Moving on to our next optimizer, we have momentum. This optimizer works well with loss functions that have steep valleys, meaning the gradient oscillates. It avoids the local minimum point and reduces the oscillations by using a velocity term instead of updating the parameters directly based on the gradient. And this helps smooth out the update steps. These two equations show how momentum updates our weight. First, it computes the velocity term, so we have v being updated to beta times our current value for velocity. And beta here is the momentum coefficient, and it typically has a value between 0.9 and 0.99. And to this product, we add 1 minus our momentum coefficient, multiplied by the gradient of our loss function with respect to the weight we are trying to update. So what this velocity term does is it allows the model to remember the direction of the previous gradients. This allows it to keep moving in the same direction of our minimum weight even when the gradient slows down, meaning that our model should be able to skip over the local minimum points, while also being able to slow down when it reaches a global minimum. To update our weight, we subtract the product of our learning rate and velocity from our current weight. Now the gradient in the velocity term can be calculated from the full batch, giving us gradient descent with momentum, or from each individual sample, giving us SGD with momentum. Or we can compute from a mini batch, and we have mini batch gradient descent with momentum. Moving on to the next optimizer on our list, we have root mean square propagation, or RMSprop for short. This optimizer was first introduced by Geoffrey Hinton, and it works well in high curvature problems, which we often encounter when training deep learning models. RMSprop works by scaling the learning rate when updating each learnable parameter based on how big or small the latest calculated gradients have been. Over time, this optimizer keeps track of the average of the squared gradients. And when this value is large, we want to reduce the size of our update so we can scale the learning rate down to avoid overshooting the solution. When the gradient value is small, however, we want to make a bigger update, and this helps speed up the learning process. Let's take a look at these equations to see how RMSprop achieves this. It starts first by computing the exponential weighted moving average of the squared gradient. And this value is equal to gamma, which is our decay rate, typically set at 0.9, multiplied by the moving average that was computed at t minus 1. To this, we add 1 minus gamma multiplied by our derivative. Once we have our moving average, RMSprop uses it to update our weight. The new weight is computed as our old weight minus our learning rate divided by the square root of the moving average plus a small number epsilon. The reason we add epsilon here is to avoid divisions by 0. This fraction is then multiplied by our derivative. And as you can see in this equation, the bigger the moving average, the smaller the learning rate will become, giving us a small change in the weight to avoid overshooting the solution. Moving on to the last optimizer on our list, we have Adam. We used this optimizer to train our model in the previous video, but we didn't talk about how it works. ADAM is short for adaptive moment estimation, and it combines ideas from momentum and adaptive learning rate algorithms like RMSprop in order to draw benefits from both. ADAM maintains two moving averages, one to track the direction of the gradients, just like momentum, and the second one to track the magnitudes of these gradients, just like RMSprop, to prevent large updates in steep gradients. To achieve this result, Adam computes the first moment m, and m at t is equal to beta sub 1 times this moment at t minus 1 plus 1 minus beta sub 1 times our gradient, which is similar to our velocity term in momentum. Beta sub 1 in this case is the decay rate for our first moving average. The second moment v is computed the same way. The only difference is that we use a different value, beta sub 2, for the decay rate of this moving average. These two moving averages give Adam the ability to track the direction of the gradient, which gives it momentum-like behavior and smooths out the fluctuations, and the ability to track the magnitude of those gradients like RMSprop preventing these updates from being too large in steep gradients. After computing the moments, we do a bias correction on them. This ensures that the moving averages are accurate, particularly in the early stages of training when fewer updates have been made. So this step helps us not overestimate the first updates because M and V are initialized to 0. Dividing each of these moments by 1 minus their decay rate gives us large values because the decay rate ranges between 0.9 and 0.99. And finally, Adam computes our weight update by taking the weight in the previous iteration, W at t minus 1, and subtracting the learning rate divided by the square root of our second moment V that has been bias corrected, plus a small number epsilon, which helps prevent division by 0. This is multiplied by our first moment that has also been bias corrected. That's all the optimizers we'll cover in this video. In the next video, we'll talk about different types of loss functions and their applications. Leave a like on this video if you found it helpful and don't forget to subscribe. Thanks for watching.